This one. Hello. Okay, so this thing is here, and okay, I need to select the window. Okay, maybe if I do this, be better. Okay. What? No. Okay. Any question from this time? So, it's very loud. Let's do this and this. Okay. Hello. Yeah. So this time we finish. Okay, maybe a little louder. Hello. Yeah. This time we finished talking about Grover algorithm. Once again, Grover algorithm is this algorithm search for this search problem. Where is our search problem? So search is an oracle problem. So given input like a function small f, and okay, yeah, the search problem is here. Okay, so we are thinking input is this small f of x, and we want to find is there some x such that f of x equal to 1, or in terms of a truth table of f of x is a big and big string, and we want to see where this big and big string has a 1 somewhere. Okay, so we want to find this mark item f of x, and in terms of classical, you need to solve this using order n query. So if you want to find a mark item, then you need to pretty much look over every bit inside this f of x. But for quantum, we see there is this Grover algorithm that use only order n queries to our quantum oracle. And the Grover algorithm, they keep doing this Grover iteration, which are two reflections. Which are two reflections in this two-dimensional space that are spanned by the uniform superposition of everything and the uniform superposition of mark item. Okay, so we see that Grover algorithm actually do keep doing two reflections, and it turns out two reflections is one rotation. So you just rotate your quantum state inside the two-dimensional state. So it will keep going in circle. So if you know this theta, then you know when the state will rotate up to around this beta, which are the mark items, and you measure it, then you will get something in beta with very high success probability. Okay, and but this requires you know the number of mark items. Okay, and if you don't know, then we have a very very brief introduction. Yeah, very rough sketch here of you can do kind of binary search. So you increase your number of iteration of your Grover search exponentially, and then you will get a constant probability of, and you get every one of them do any one of those constant times. Then you get a constant probability of actually catch your mark item, no matter what number of mark item you have. And because this sequence is increasing exponentially, and the time, the extra amount of time you need to run is like a sum of geometric series, and they converge, and you only get the extra constant factor. Okay. And but other way to do this is you use something cooler. Is you can use quantum counting. Okay. And so quantum counting is actually something more powerful than Grover search. And so in Grover search, you only want to find the mark item. And but in quantum counting, you want to estimate the number of mark items. Okay. and so how much query you need to do, you need to use for quantum counting depends on how accurate you want your estimate to the number of marked item m here is. And here we parameterize the error by multiplicative error. So that means we allow the error in number of marked items to be epsilon times the total actual marked items. Okay? So delta n equal to epsilon times m. And so this delta n is the additive error. Okay? And then we show that we want to show that there is a quantum algorithm that do quantum counting using 1 over epsilon square root n over m queries, okay, to the Grover oracle. Okay. And the idea, okay, so this is more powerful than Grover algorithm, and but anyway, so if you use low enough precision, then if you use low enough precision, then this will allow us to give a rough estimation of this m and to do Grover algorithm. So the textbook do this kind of wrong. I guess it's not wrong, but kind of badly. Okay. So textbook use order n. Okay. So the dump here. So we prove this is possible, kind of, and but anyway. And so we prove the similar thing. We say that so if you use order n queries, okay, so I guess we probably can do a similar thing here. We can probably rewrite it here. Okay, so what textbook pick is they use order square n query here. Okay, so if this is equal to order square root n, then then you have epsilon is about so this is square root over n, then 1 over epsilon equal to 1 over square root n. So epsilon is about 1 over square root n. Okay, and delta n will be about yeah. I guess this is enough. Yeah. So epsilon will be about 1 over square root n, and then this will be good enough. So if you have your m relative error m is 1 over square root n, so it's less than constant, then this will be enough to do your Grover search. So yeah, so the idea is you use quantum counting with this many query, then you get n to this relative error, and then you just use this number of steps. So you just rotate your Grover search with the m you estimate, then you will have a very good probability of getting marked item in your Grover search. But the problem here is that this thing is square root n instead of square root n over m. Okay, so you are losing something for this quantum counting approach the textbook describe. Okay, and yeah, but that's something you can do. So this thing is actually a bit more efficient than, yeah, I guess a lot more efficient if the m is larger. Okay. So this is actually more efficient than the quantum counting approach the textbook describe. But this is something you can do. Okay, and but okay. But anyway, quantum counting itself is pretty useful, so let's go to see the detail of it a little more today. But I guess before we go to detail, any question? Oh, I can say a little higher thing. Okay. And the quantum counting is really related to Grover search, because what we do is we do phase estimation on the Grover iteration tree. So basically, Grover iteration is a rotation by angle theta. So if you write down it in this alpha beta basis that we always care about this two-dimensional space, then G will be cosine theta minus sin theta, sin theta, cosine theta. And then you calculate eigenvalue of this thing is ei theta and ei 2 pi minus theta. So if you do phase estimation, then you can basically learn theta. You either learn theta or 2 pi minus theta, but they're basically the same. Okay? So you will learn theta, and you will have some error on theta, and then the actual hard calculation is how delta theta related to delta m, where m is the number of marked item we actually care about. Okay. So that's a high-level idea of quantum counting. Any question? Okay. If not, Then yeah, let's go to the detailed quantum counting. So this is what we do. Okay. And okay. Yeah, so let's see how delta theta actually related to delta m carefully. So this time we have a really rough estimation of how delta theta relates to delta m. We assume delta theta is very small and the delta m is very small. And we kind of use this calculus approximation, and we see that delta m is about the square root n delta theta, or the square root n delta theta, and yeah, then we get our estimated result. But let's try to make everything finite and still calculate it. Okay, so yeah, so we want to estimate the theta because the eigenvalue is of this thing is ei theta. Okay, and we do phase estimation. We'll get the estimation of theta with some area delta theta. Okay, and before everything, we assume we take n to 2n. So we double the number of n so that the theta is less than pi over 2. So when we deal with sine and cosine, they are a little easier. Okay, and yeah, this you can do by just append zeros. So you just add more zeros to your truth table, append a whole bunch of zeros to your truth table of your function. So you kind of made the space of your function twice and make a lot of than 0. Okay. And also delta is the error probability. Then we pick the parameter of our phase estimation. So we say we use t equal to n plus this log 2 plus 1 over delta bits in phase estimation. Okay, and so this will tell us two things. So and this we have some m and m to be fixed. Okay, so we'll fix on delta that we want, and then we have like this n that to be determined later. Okay, and so here we have t here, then t already determined the number of query. Okay, so number of query, if you think of phase estimation, they need to call this control oracle, and there is control up to, and there is t bits here, and so the first register is like 1 to 2 to the t, and I guess 0 to 2 to the t minus 1. Okay, 0 to 2 to the t minus 1, and so this j here is 0 to 2 to the t minus 1. So you can call your unitary up to about 2 to the t, and so number of query is about 2 to the t. Okay, and also it tells us the precision on m. Okay. So this formula is from the Shor's algorithm here, the phase estimation here. Where do we have phase estimation? Oh, it's another. Okay, never mind. Not this one. But yeah, so when we talk about phase estimation, we say we use these many bits, then we can get n bits precision and with error probability delta. Okay. And yeah, okay, so we can use 2 to the t query to get n bits precision with delta error, and but we also need to use a good eigenstate for our unitary. So basically, we need a superposition of eigenstate inside this subspace where G is actually the two-dimensional C. And that's easy because we know the uniform superposition is inside this two-dimensional space. Okay, so it's inside this two-dimensional space, so it will be the linear superposition of either this one or over this eigenvector of this and eigenvector of this. Okay. So we use equally this side state as equal superposition of everything. Then when we do phase estimation, we should get this thing is inside this two-dimensional space, so we should get either this theta eigenvalue or 2 pi minus theta eigenvalue. Okay, and yeah, so we'll learn theta over 2 pi minus theta, and now theta is and with this precision, as we say, n bit precision, so it means delta theta less than 2 to the and the error probability 1 minus delta. Okay. And because theta is going to be less than pi over 2, and so it's very obvious. So theta is something between 0 and pi over 2, and so it's going to be look very different from 2 pi minus theta. So when you get 2 pi minus theta, you can just flip it to theta. Okay, just have 2 pi minus this thing, and it becomes theta. Because this thing will be between 2 pi and what's that? Yeah, 3 over 2 pi. Okay, so those are very different range. So if you see something in this range, then you just flip it to this thing. Okay, so now we just assume we get theta. Okay, and yeah, now let's do the calculation. So how is theta related to m? So now we have theta with some delta theta less than 2 to the m. And now we want to find delta m. So we have this equation related to theta, and n is sin squared theta over 2 equal to n divided by, okay, it was n, but we make n to 2n, so it is m divided by 2n. Okay? Yeah, this is just because we double the n before. Okay? So this is a little confusing, but now it's this thing. Okay? And now we think about, so kind of follow this idea here, but yeah, but now we think what's the delta n divided by 2n. So so what's delta n divided by 2n is m plus delta n minus m, then divided by 2n. Or I should say this is m minus delta n divided by 2n, and n divided by 2n. Okay, and but n plus delta n divided by 2n will be so if you have m here, it should be theta, and but if you have m plus delta m here, then it should be theta plus delta theta here, right? Because we are thinking how are the m change when theta change. Okay, so this thing here is m plus delta m divided by 2n and minus n divided by 2n, and the absolute value. And so this first term will correspond to sin squared theta plus delta theta over 2. And the second term should be sin squared theta over 2. Okay? Because this is m divided by 2n is just this thing, and this is you change m to delta m, so you should change theta to plus delta delta theta. Okay? And yeah. Okay, then now. So now we have this thing, then the rest is just math. Okay, so we need to do a whole bunch of trigonometry to bound this thing. Okay, and first we have just a squared minus b squared is a plus b times a minus b. Okay, so sin squared minus sin squared, then is sin plus sin and sin minus sin. Okay, and okay, and then now we use yeah. Then now we use the fact that our theta is between 0 and 2 pi, so the sign is positive. Okay? So positive, and so we should have absolute value here, but it's positive, so we get rid of positive. Actually, do we? Maybe oh, actually we don't need that, so maybe I'll just draw this better. I think we can just have. Although it's yeah, so when we just have absolute value sign here. Okay, and so we have absolute value sign here, and anyway we have sin plus sign and sin minus sign. Okay, and then we bound each term. So we bound the sin minus sign term first. Okay, and sin minus sign first we use this formula called product of difference, or I guess the Chinese name I know better is 和差化剂. But anyway, this is sin A minus sin B equal to cosine A plus B over 2 and sin A minus B over 2. This is one of the trigonometry formula that you probably learned in high school. And yeah, so sin A minus sin B, then we turn to cosine something and sin something. And let's check the cosine something correct. So cosine A plus B over 2. Okay. So those both have sin theta over 2 and delta theta over 2 become delta theta over 4. And sin A minus B over 2. A minus B is delta theta over 2 and divided by another 2, so delta theta over 4. Okay. Okay, and then we want to upper bound this thing. And so we just upper bound the cosine part by 1 and sine part. So we have sine x is less than equal to x. Okay, so sine we just upper bound by sine delta theta over 4, we just upper bound by delta theta over 4. And keep the absolute value. And finally, okay, finally this is totally extra thing, but yeah, then we just actually we don't need this to be 4, so we make it 2. Okay, this is just whatever. And okay, then what about the first term? Oh, actually we are still not doing absolute value. Okay. I guess it's wait. Oh. I think we are doing more like this thing. It's a bit funny. Okay. So it's the absolute value and okay, that's still absolute value. Okay, so absolute value of those two terms is going to be less than like sum of so absolute value of this plus absolute value of this. Okay. Yeah. And okay, so let's think about what's the absolute value of this term here. And well, is so we use the trigonometry formula again, and it's going to be less than equal to yeah, it's not very important, but anyway, so we bound the absolute value of this term first, and it's going to we use basically reverse of this formula. So sine a plus b equal to sine a cosine b plus cosine a sine b, and so a is theta over 2, b is delta theta over 2. Okay, and okay, so sine a cosine b cosine a sine b, and this is less than the absolute value of each individual term, and okay, and once again we get rid of cosine. So less than absolute value of each term, and we get rid of cosine. And I guess here is where we use theta is less than pi over 2. So then we say sine theta over 2 is positive because theta is in a nice range. So sine theta over 2 is positive, so the absolute value of sine theta over 2 is just theta sine theta over 2. And the next term, once again, we just upper bound cosine theta over 2 by 1. And then we upper bound this sine delta theta over 2 by delta theta over 2. And we take absolute value here. So delta theta is actually can be negative. Okay, delta theta is positive or negative. And anyway, then now we have everything together. So now we put everything together and now I put everything together. So this thing is upper bound by, so the first term, this one becomes sine theta over 2 plus delta theta over 2. And then this one absolute value once again is positive, so it's another sine theta over 2. So we have twice sine theta over 2. And then is delta theta absolute value over 2 here. And the next term, as we say, is delta theta absolute value over 2. Okay. So you see that we get things similar to, where is it? So we get similar to this thing. So here we have square root 2n delta theta. And here we also have delta n to something theta, but we get the extra term. So our careful calculation gives us this second order term. Okay, so this thing will give us our square root n term, and so delta n is about delta theta, and so if you put n here, this will give you about square root n. And but now we are a little more careful, so we also get this second order theta term. And we are going to try to argue that this second order is not too important. Okay, but anyway, so we have this sine theta over 2 here, but we don't want to express things in theta, and so we turn this into the m and n again. So sine squared theta over 2 once again equal to n over 2n, and And then we know delta theta. So delta theta already have upper bound. Delta theta upper bound by 2 to the minus m. So these two things. So you change the first term here by this equation taking square root. So now is the sine part is square root of n over 2n, but you put 2 inside, so square root of 2n over n. Okay, and all the delta theta become 2 to the minus n. And you divide by another 2, so it's 2 to the minus n plus 1. 2 to the minus n plus 1, 2 to the minus n plus 1. Okay. And yeah, then finally you multiply this 2n to other side. Then you see, so delta n is equal to square root. Wait. No, I'm a little confused. Did I do the calculation a little wrong? Okay, so it's n get twice and 2, so I think we are missing one order. Okay, wait. Okay, I will check the textbook again. But I think so there is a 2 here, so we should get another 2, so we should cancel these 2 and this should be no plus 1 here. Okay, but anyway, that's not too important. We care about big O. Okay, and yeah, so this is everything. So you multiply n on each term here, and then you got this thing. Okay, and so once again, as I say, you get this square root 1 term. So it's like this square root 1, then we got second order term n over 2 to the n plus 1. Okay. And yeah. And so this is error bound on quantum counting. Then you can pick now you can pick a different t. Then it will give you different m and different small m, and that will give you yeah, that will give you small m, and that will give you different delta m. Yeah. And so let's see what happens if we want delta m equal to s on m. And then we see that so we want a constant relative error. Okay. And then we have so if we ignore the second order term first, then we will have s on m is about 2 to the minus m times the square root nm, and let's forget these 2. So about order 2 to the minus m times square root nm. Okay. So we'll have 2 to the n is about 2 to the n, so put this side equal to 1 over epsilon, and n dividing here, so square root n over n. Okay. So on the first order approximation, we see that the number of query we need to make, which is about 2 to the t, and which is about 2 to the n times order 1 over delta. And but we are ignoring order delta term. And so we see the number of query were about 1 over epsilon square root n over n. And we can put this equation in, this number inside the second order equation again, and check out the second order term. So you put this inside, then you see that the second order term is epsilon square n. Okay, so the second order term is okay as long as epsilon is obviously less than 1. Okay, so your delta m is still order epsilon m. Okay, I guess it's a little funny because now your epsilon got some correction, but yeah, but if your epsilon is small, then this is okay. Okay, and but now there is like a subtle funny thing. Subtle funny thing is if you want this constant epsilon, then you kind of need to know m. Okay, but as you say, the textbook say, well, we don't know m, then we can pick we don't know the big M, then we can pick a pretty good small m. So more likely pick a t. So we can pick t to be square root n, then we'll get this epsilon will be about 1 over square root m. Okay, or delta n about order square root m. Okay, and yeah, so here are something that will happen. So if we pick, if you want a constant additive error, then number of query is actually a lot, square root mn, and and then the textbook pick is if you use quantum query about square root n, then you can get delta additive error about delta square root m. Okay. And finally, this is quadratic. So this number is a quadratic speed up over classical. Okay. So classically, you can prove that if you want this epsilon relative error, then you need 1 over epsilon square n over m queries. Okay. And then finally, then there is this recent research. I guess not so recent anymore. It's about 4 years ago. Yeah. Yeah. So there are several things that people are unsatisfied with this. Okay. So first thing is, well, you can see we have this rainbowing about you need to know m here to make a constant epsilon error. Okay. And then another thing is people just don't like phase estimation that much. Okay. So because I'll say this. Because this is the quantum counting, you can see it should be about global search. So you kind of feel that you should be able to do this by just global search. And also, for more practical reason, phase estimation is not easy to do. Okay. Yeah. So because we have the current near-term quantum computer is not so good, and yeah. And we find out that to do phase estimation is not easy. Okay, so we are thinking, can we just kind of do binary search to do quantum counting? Because kind of like here, so you see that we can do, although this is global search, we can see that we can do this kind of binary search thing to do global search without knowing the number of mark item. Then maybe we can do quantum counting also with kind of binary search to estimate n nicely. Okay. And that's indeed possible, and that's this recent paper do. Okay. So we do quantum counting without doing quantum Fourier transform, and we don't need to know n beforehand to get a constant error. But there is a little overhead in computational complexity. It's order log n. Okay. Okay. So that's about quantum counting. Any question? If not, then yeah, we are in a bit funny time. And yeah, so here this is not too important. So this is just a rebar back to NP-POMP problem again. But we were talking about so we actually will talk about application of global algorithm later. So next class we will start proving the lower bound of global algorithm, but here we will talk a little bit about what we can do with global algorithm. Okay. And yeah, so I guess this should really come before we actually talk about algorithm. But anyway, so this thing is, but we already talked a little about this. So we say we can use global algorithm to sometimes speed up solving NP-COMP problem. And the idea is NP-COMP problem, they have efficient verification. So if a yes instance of a NP-COMP problem, you can check this efficient algorithm M that will check whether your X and witness are get accepted. So for yes instance of your NP problem, there is a small witness W, and you can efficiently check this W witness is verify your X. Okay. And yeah, and so this M is well, this M is an efficient classical algorithm. Then you can build a quantum version of it. Okay. And then you can think about it as a quantum oracle. Okay. So you can use this M as a quantum oracle. Okay, so I guess you fix X. So you have this n sub X, then it's now a function of W. And so the function of W will check whether your W gets accepted or not. Then you build this as a quantum circuit, and then you run it as an oracle, and you can do global search. Okay, so you have the f of w is you fix on x. So this f actually depends on x, so it's kind of like f sub x. Okay, so it's like f sub x of w. Okay, and yeah, so you can build this as a quantum circuit, and then you think it as a quantum oracle, then you can do global search on it. So you search whether it's a w get accepted by get accepted with x by this n. Yeah. And yeah, so you do global search, then you will need square root to the total number of w. So now we say w is an empty string, so you need to do it over encode. And if you are to searching these brute force classically, then it's 2 to encode. Okay, so it seems faster than classical brute force, and yeah, that's an improvement. But there is a caveat that we're going to see a bit more detail later. It's just that there are smarter classical algorithms than doing this thing, and so this doesn't necessarily give you a quantum speedup for solving a p-complete problem. Okay, and yeah, we are 5 minutes early, so I gotta stop here now, and we'll have a 10-minute break, and then we'll start doing our lower bound. Okay, let's have a 10-minute break, and then we'll start next class a bit early. Okay. get back. Okay, let's get back to this most technical proof of the course. But we probably cannot finish this, so you will need to wait for 2 weeks to see the later part of it. Okay. And yeah, so this is the most technical proof of this course, and this is kind of why theorists love Grover's algorithm, because we can prove a very clean and tight lower bound of it. Okay. But so first there is some confusion about this. So we are talking about we say it's a lower bound for Grover algorithm, but it actually is not something precise. So what we are actually lower bound is a lower bound for search problem. Okay. So we are proving the optimality of Grover algorithm, and this actually means that so if you have any algorithm that solves the search problem, okay, and once again let's go up here. So it's about here, right? Yeah. So this is a search problem. It's a problem of you are given this oracle of small f, and you want to find a mark item. And so we see that Grover algorithm can find a mark item in order square root n time, and we want to say any algorithm, so not only Grover algorithm. Okay? So if you construct any quantum algorithm, then it's actually not much better than Grover algorithm. So we'll have a omega square root n time, omega square root n lower bound for any algorithm that solves the search problem. And okay. And so this is actually a query lower bound, and which in turn will also be a time lower bound. Okay. So we are lower bounding the query complexity of solving the search problem. So the search problem, we say any quantum algorithm solving it, you must use omega square root n query. Yeah. And to make this look a bit non-trivial, so think about it. So it's a bit weird because the quantum query can kind of query things in superposition. So remember our oracle kind of we think about it's like a black box. So it's our oracle is the truth table of this function. So from f0 to fn bigger minus 1. Okay, and so if you want to do classical lower bound, you can kind of ask, well, you need to know enough number of these blocks. You need to look at enough number of these blocks to actually compute your big F. Okay. So to actually compute, say, your search problem. But quantumly, then you can use equal superposition. You can use like a superposition query to kind of look everything together. So it's harder to say how much you need to look at this box, because you can kind of look at every box by just uniform superposition query on everything. Okay. But still, we are able to do this thing. Okay. But here, first small notation. So once again, we have this small. So we have this small f, and that is the input to this problem. Okay. So here we have kind of two functions. It's a bit confusing. So we have a small f, that's the input to our problem. So our problem is this search, and we also have this big F. Okay. So big F is the search problem here. Okay. So big F is this search. Okay. So small f is this truth table, and the big F is the problem we actually want to solve, which is search. Okay. It's ugly. Okay. So let's erase this. Okay. Yeah. Okay. So we have small f and a big F. So we want to calculate big F of small f. Okay. So given some small f truth table, and want to see this big F, I can find a mark item. But actually, for lower bound, we might want to make things a little simpler. So this is also something we said. So now is where we use the decision version. Okay. So before our big F, it was that if there is a mark item, you need to output the mark item. But let's make things a little easier. Let's say our algorithm just needs to say is there a mark item or not. Okay. So now the big F becomes a decision problem. So is yes or no. So yes is there is no mark item, and no is there is mark item. Okay. And yeah, so we want to lower bound this decision version of Grover. So just decide where there is a mark item in small f or not. Okay. So basically, where it is an O0 string or there is a 1 somewhere. Okay. And yeah, then we want to do quantum query complete lower bound for this big F, this decision version of the search problem. Well, I guess it's the decision version, so it's not search. So the decision version of Grover problem. Anyway, okay, and here is okay. So we are thinking about quantum query complexity. So we want to lower bound the number of query. And here we describe a very general scheme for doing quantum query lower bound. Okay, so first we wrote down this schematic for quantum query algorithm. So we say you start with the O0 state and you do whatever unitary that doesn't depend on your input small f. Then you do oracle, then you do whatever unitary, and then you do oracle, etc. So here we are actually being a little unprecise, so this is a bit confusing here. And so what's confusing is that you can actually have some ancilla here. Okay. And yeah, so you can use some ancilla and your unitary is doing some bigger space than your oracle. Okay. But yeah. But we will kind of ignore this for now and argue that it's okay later. I guess actually we're not in this PDF, but we'll probably argue in homework. Okay. And anyway, but the important thing for now is that you have unitary oracle, etc. Okay. And what we are going to track is how the state change. Throughout this algorithm. Okay, so and how that depends on your input function small f. Okay, so we'll define those time slices of your algorithm. Okay, so we say after you apply this first u0, then this state we call it psi f0, and then this state then you apply an oracle, then another u1, and this state called psi f1 and etc. Okay, so kind of after each oracle and whatever unitary pair you get, we look at the time slice and we call it psi f2. So it's psi fk after like basic case oracle code and HR unitary. Okay, and yeah. Okay, so we want to compute something on those things. Okay. And the idea is that, okay, so different f will give you those different psi, okay, but okay, yeah, so different f will give you a different psi, and we want to consider so this distance between different psi, okay, yeah. Yeah, distance between different sides. So there are multiple distances you can choose, and the distance we choose here is kind of funny distance. So it's non-square of those two vectors. Okay, and yeah, so we have f and f prime, and we care about the distance between the psi ft and the psi f prime t at some time step t. Okay, and non-square. And the particular choice here is not too important. You can also do this with just inner product. Okay? Because you see, well, basically the inner product is linearly related to this. Okay? But anyway, this is what we'll pick. And so what happens is that this distance is increasing throughout your algorithm execution. Because at the start, before you do any oracle call, then all those psi ft should be the same, because so it doesn't depend on f at all. Okay, so the psi f0 is the same for every f. It's just a u0 apply on 0. Okay, and okay, and at the end, then sum of the psi ft must be different from psi f prime t. Okay, because at the end you need to be able to distinguish between yes case and no case. Okay, so yeah, so if your f and f prime is one of them is yes case and one of them is no case, so basically means when the input into big F is different, Okay. Then in the end, these two quantum states must be far away. Okay. They need to be far away so that you can do a measurement and have a good probability to distinguish those two different states. Okay. And yeah. Okay. So now we consider this f and f, some f and f prime pair with different yes and no value. Okay. And yeah, so they start all the same and end up being different. Okay. And so if we can say in the middle they cannot change with each query, then we are good. Then we can say that you start with zero distance and you end up with a lot of distance, and in the middle the distance cannot change too much. So each step in the distance cannot change too much. Then you need to do a lot of steps to make the distance large. Okay, so that's kind of the idea. Okay, okay, and and also noting. So first to make this sensible. Okay, so first make this sensible is that you notice that those u doesn't change the distance. Okay, because u doesn't depend on f. So when you apply u, then this thing got a u here and this got a u here, and this distance non-square just doesn't change. I think we have calculation here. So yeah, so basically unitary preserve distance. So if you just apply u on both psi f and psi f prime, then the distance doesn't change. Okay, and so the only way to change the distance between psi f and psi prime is you actually apply OF, because OF is different from OF prime. Okay. Okay, so psi f and psi prime, they need to separate each other. Okay. But it's not so simple to just pick one f and one f prime to see, and we can lower bound the quantum query complexity. That's because if you just fix on one pair of f and f prime, actually one query can differentiate them, because there will be. Okay, so it's a lot of detail, but I think we don't need to go into detail. But basically, if there is some f and f prime, and then you think about the truth table, there's something different, somewhere different on the truth table, and basically if you query that different location, then you'll distinguish f and f prime apart. Okay, so one query will distinguish any f and prime. So what we actually do with distance is we sum over average of a whole bunch of different f and f prime pair. Okay, so we'll sum over some f that give you yes. Some f that give you yes answer, and some f prime give you no answer. Okay, and now kind of so we want some set of f that give you yes answer, and a set of f prime give you no answer. Okay, and okay, so now we go back to search a little bit. So what well, the only yes answer input to search problem is O0 string. Okay, as we know, because this is the only thing that with no mark item. And then this part is where you need to be creative for different problem. So what is f and f prime set you pick, it depends on your problem. But anyway, for proof here for search problem, we'll pick f is the only yes instance, and f prime is the thing that looks most like the yes instance. And that's one that's everything that has only one mark item somewhere. Okay, so there are n different possible f prime here that we are using. Okay, so it's okay, yeah. So so it's it has one mark item and some location x here. Okay. And yeah, and so our actual distance we are tracking is the sum of distance between all those between this f and all those different f prime. So this is f prime with mark item on first one, and f prime with mark item on second one, and all the way to f prime with mark item on this one. Okay. And then we will show that when you use one quantum query on this thing, when you use one quantum query, then the sum of all those distances cannot change too much, and you will only yeah. So the sum of distance will need to change from kind of, so we can do a quick counting. So sum of distance. So let's start with 0, and the end all of that need to have a distance about constant, so about order n. Okay, and each step will change. So each step will change about order square root n, and then you need a square, like omega square root n steps to change the distance from 0 to order n. This is what we will do. Okay. And any questions so far? That's a high level idea. Okay. So yeah, so we sum over these n distance pairs, and then we need to show that each query only changes the sum of distance by order square root n, basically. Okay. If there is no question, then we will continue and see how much we can do today. Okay, so let's do this with actual numbers. Okay, and yeah, so as we say, we'll look at this f as yes instance as O0, and f prime are those one mark items function. Okay, and so we give them a little more names. Okay, so the O0 f, we call it f tilde of 0. Okay. It's a bit funny. We have a tilde here because there is another f0. Okay. And for this one mark item somewhere, then we give it a name. Okay. So this thing is, oh, I forgot this. So maybe I'll use red so I remember. Okay. So this thing is f tilde of 0. Okay. And for x in 0 to n-1, so all the possible location, then we define this f sub x. That's just you have one mark item at the x location. Okay, so now it's just notation. We are just keep calling this thing as this string as f tilde of 0, and so this is f0, f1, all the way to fn minus 1. Okay, and yeah, so we need tilde here because we have another f0 here. It's just notation issue. Okay. Okay, yeah. So this f sub x thing is associated with this truth table where you only have one mark item at the x location, and all the thing is 0. Okay, so you have a unique mark item. Okay, and yeah, so as we say, we want to compare all n pair between f tilde 0 and f sub x. And okay, and so I guess a lot of things that you need to check later. I think it's not even in homework, but yeah, but I guess that's still marked as homework to check later by yourself. But maybe we will not actually do this in homework. Okay. Anyway, so for now we assume the oracle we use is a face version. Okay. And we ignore the control register, but I just it can only also be done with control register. So for now, to just showing how this method works, we make the oracle a little worse. Yeah. And yeah, okay. So our oracle will do. Okay. Yeah. So we ignore the control register, and we also assume. Wait, do we see that somewhere? We also assume we didn't use NC. Okay. Also assume no NC. So to simplify the calculation a little bit, okay. So we assume no NC, and we assume there is no control on your oracle. So we restrict the algorithm a little bit, but it can be easier extended to these two cases. Okay, so back to a proof. So we have a face version of our oracle. So what does the face version of the oracle do? Okay, and so we think about what are the oracle related to those f, this f tilde 0 and the fx. Okay. So oracle for f tilde 0 is it will do nothing because there is no mark item. It's going to be identity. So remember the first version of Oracle, it does, okay, we should have here. Do we have? We should have. Yeah, so first version of Oracle, it do this is -1 to the f of x. If your f of x is 0 everywhere, then yeah, if your f of x is 0 everywhere, then this is just do nothing. You just get x back always. Okay. Yeah. Okay. And what about this? The other Oracle. Wait, what's going on? Oh, I see. Yeah. What about the other one? Okay. So the the unique mark item Oracle, it also almost does nothing. Okay. You only get so you also use so maybe I'll just write this here again. So remember OF 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 on x equal to -1 to the f of x. Okay. So think about what they do. Okay. So y now is a computational basis state. So what does this do on computational basis state? Is it something from 0 to n-1? Well, if this state is not equal to this x here, then it does nothing. Okay. And if equal to x, then you apply -1. So you can write this as delta xy. Okay. And but the better way to write this is the projection that we keep talking about. Okay, so you can also write this as not projection, sorry, reflection. So we say go over like this thing, right? So we say the go over Oracle is a reflection around the mark item. So kind of where? Yeah, I think it's this thing. Yeah, so the global Oracle is I guess saying global Oracle is a little weird, but this Oracle is a reflection. So this face Oracle is a reflection around the mark item, and yeah, so you see only x state get -1, so it's a reflection around x, and so it's identity on everything, but you get -2x. -2 projection on x, so you have x here, then you have 1 -2, you have -1 face. Okay. Yeah, so we want to have, so we know all f of x is actually this form. Okay. So because it is true for every computational basis state, so we know all f of x is actually just this thing. Okay. And then we make the notation a little easier. Okay. So make a notation a little easier. So instead of all f sub x, we just call this all x. This is just making notation easier. Okay. And all x equal to this thing. Okay. And then just as I said, we assume our algorithm do this. We start with 0, then apply unitary, oracle, etc. And we say after case unitary here, we say the state is psi fk. Okay. But our f only have these two possibilities. We have x and f tilde 0. Okay. And so for the x1, we call the psi xk. Okay. Because then we just keep writing this f here. Okay. So the state after k is oracle call then unitary, and where your f is has a mark item x coordinate, then it's called psi xk. And if there is no mark item, then we know the oracle is just identity. So your state would be just the product of those unitary, and this state we call it just psi k. So we just we just ignore all the upper script and we call it psi k. Okay, so psi k corresponds to the ES instance, and this is one of is a no instance with x marked. Okay, and both of them on case step. Okay, And as we say, the progressive function is the distance between those two things and the sum over all possible x. Okay. And yeah, so distance between those two things is difference of those two vector non-square, and you sum over all possible x. So x from 0 to n minus 1. Okay. And yeah, then we call this thing dk, d sub k, and k is basically after k's query, k's oracle call. Okay. Although there is a extra unitary, so not precisely, but you can only get this after k oracle calls. Okay. And yeah, then we get a bit more lazy, so we don't even write cat here. Okay. So we just get rid of cat here, and we write psi k dot psi. Okay. So our dk is this non-square psi sk minus psi k. Okay. And sum over all x. Okay. And finally, we want to say, okay, so we want to say two things. So first thing is this dk cannot grow too fast. Okay. And the second thing is the dk must end up with something big. Okay. Okay. And so first part, okay. So I guess it's a little different than what we can. Okay. We can dk step is omega square root. I guess it's similar, but actually what we say is dk grow at most quadratically. So dk will grow like order k squared. And at the end, dk is omega n. And this is kind of easy to see because you can kind of feel that this should be constant for every pair. So you sum over n pairs, so there are omega n. Okay. And yeah, so if you want k squared to be n, then k will be square root n. Okay. Okay. And then let's prove the first part. So first part we prove by induction. Okay. So we want to say, so actually we have exact number here. We prove dk is less than equal to 4k squared. We got this kind of well, this is 4k squared kind of because we know the answer. So these the numbers are picked because we know the answer. But anyway, so yeah. So the proof is a bit unintuitive because this proof is written when we already know the proof result. But anyway, it's a proof by induction. So we say we want to prove dk squared is less than equal to 4k squared. So by induction, we first check the first step when k equals 0. Okay. So k equals 0, dk equals 0, and it satisfies this. Okay. And then we now do the actual hard step. That is induction step. So this is true, and we want to say this is also so this is true for k. Then we want to say this is also true for k plus 1. Okay, and yeah, so let's see how it goes. So dk plus 1 is sum over this x, and psi k plus 1 minus psi k, and what is psi k plus 1? Okay, so we'll scroll up. So psi k plus 1 is this thing with one more step. So we'll put another OX and UK plus 1. And also what is it? So the psi k plus 1 sub x, sorry, psi x sub k plus 1. And what psi sub k plus 1 is you just get extra UK here, k plus 1 here. Okay. And yeah, so on the psi k thing, you get extra UK plus 1 and OX, and on psi no superscript thing, you just get extra UK plus 1. And then here we use the thing we said before. So this UK plus 1, it doesn't depend on x, it doesn't depend on f, so basically it doesn't depend on x here. And so this is same for, yeah, so this is kind of like a constant here. And this thing just doesn't affect the norm here. Okay, so you can cancel this UK plus 1. Because it's a unitary it's the same unitary rotation on those two vectors. Okay. And yeah, so UK plus 1 doesn't change the distance at all, and the only distance you change is this OX. So psi xk will get extra OX, and psi k get nothing. Okay. And now we do something funny. Okay. we do something funny kind of because we know the answer, so we do this thing. Okay. But anyway, we want to break this difference to two difference that's easier to bound. Okay, so we are basically adding, abstracting. So we are basically do plus minus O sub x psi k. So we put kind of mixing those two things together. Okay, so we take a difference between O sub x psi x k and OX psi k. Okay, so we have the minus OX psi k and the plus OX psi k here. So kind of between those two states. So we kind of break up the distance to two distance. So we have OX psi x here, OX psi x here, and psi k here. And we say this distance is basically is going to be less equal to the distance to OX psi k. This distance is going to be less than this distance plus this distance. Okay, and so you have OX psi x and OX psi x k minus OX psi k, then you have plus OX psi k minus psi k. Okay. And but you see that each one of them is similar to this. So you can take out OX here and then you can take out psi k here. Okay. And so you have this distance equal to those two distances summing together, but you also have non-square. Okay. So now remember this is vector, so we call it B and C. So we have a B vector plus a C vector non-square, and it's going to be less than or equal to B squared plus 2BC non plus C squared. Non C squared. Sorry, it's a typo here. This square should be outside. Okay, non C squared. This is just, I don't know, linear algebra. Okay. Okay, so let's bound. So we basically need to bound the non B and the non C, and there is still summation outside. Okay. Anyway, we'll need to bound non B, non C under summation. Okay. And so the first thing we do is deal with this C term. Okay. So what is C term for some x? And now we actually look back to our OX. Okay, so OX minus identity is minus 2x project. This is minus 2x projector, because remember we say our OX is this thing. Maybe let's just write it here once again. So here we use the derivation we had before. OX is identity minus twice xx. Remember we say OX is reflection around x. Okay. So in minus identity, then you just get this projection on x part. Okay. And so this thing is minus 2 and the inner product between x and psi k and x. Okay. And how about the first part? The first part, okay, so if you think about non b squared, then okay, so this is a bit funny. So non b squared, you have OX is also a unitary. So if you take so this b squared equal to some x OX psi xk minus psi k, right? And square. But so you think about this non. So if you fix every x, then OX is a fixed unitary. Okay. So it's a fixed unitary. So actually this OX also doesn't do anything because you have non. Okay. So OX doesn't. So when you fix every x, because you fix x and you take a non square, right? So inside you can fix x and take a non square. So inside is non square, OX is a fixing, and so it's just a unitary, and so unitary doesn't affect the non, and so you can just take all the OX squared. So b squared is just psi sk minus psi k squared, and okay. So that's b b squared. And so think about this sum over x. This is actually dk. Yeah. Right. Remember, dk is dk is this distance. Okay. And so that's dk. And then we write down everything else. Okay. And we have 2bc. Okay. And okay. So 2b and b, as we said, well, is known. Although it doesn't have square, then it's known still can take out the ox. Okay. So maybe let's just write b here. Okay, it's a bit confusing. Never mind. Yeah, but you can. So everything actually this thing, everything is here is like x. Okay. So maybe let's not write some x here. Okay. Let's say all those things are like depend on some x. Okay. This is a function of x. So we think we do those calculations on fixing some x. Okay. So b squared is this thing, then you sum over x, then this is dk. Okay. And then I would say, so b is this thing, is psi xk minus psi k, and c is this thing here. Okay. And so c is this thing. So when you talk known on this thing, then you get a 2. So this 2 times this 2 becomes this 4 here. And then here, the x is a normalized state, x is a computational base state. So norm of x equal to 1, then you get the extra absolute value of the inner product between x and the psi k. Okay. And yeah, so maybe let's write here. Actually, maybe this is better. So let's write norm b is this thing. So norm b you don't have this ox, and norm c equal to from here 2 and twice the norm of x inner product with psi k. Okay, this makes things a little easier. Okay, so because you take a norm, then minus 2 beyond 2, and you take a norm on this thing, and norm of x equal to 1. And the norm on b, as we say, you can take out the ox. Okay. Okay, that makes things a little cleaner. Okay, so 2bc is this thing, and c squared is 4, and this inner product square. Okay. Okay, and now what will happen? So now we will simplify a lot of things. So the b squared term, as we say, is going to be dk. And the c squared term, actually, when you sum over x, it becomes 1. Actually become 4. Because this is the amplitude of psi k on x coordinate, right? And because psi k is a normalized state, so we sum over all those. So the coefficient of psi k on the x coordinate. So sum of coefficient squared should become 1. And if we want to see this in more algebra, then this. So sum x is the inner product square. Is this inner product times its sum x is inner product times its complex conjugate. And the only similar x is the thing inside, so you can put sum x inside for this sum x. And sum x is just identity because x is all computational basis state. So the inner product being psi k and psi k is 1. Okay. So c squared term become 1. Okay. And b squared is dk. And so how about the middle term is bc term? The bc term you can just do Cauchy-Schwarz to say is the square root of this thing times this thing. And here we have the proof. So sum x over sum ax bx is less than. So Cauchy-Schwarz inequality say sum x over sum ax b a sub x and b sub x is less than. So the inner product is less than the norm of a vector and times norm of b vector. And the norm of a vector sum x ax squared and the norm of b vector sum x bx squared. Okay. And yeah. And so this is sum x, then you have ax bx is less than square root of ax squared. So basically sum x ax squared, so basically sum x b squared. So it's gonna complete. So ax is this norm b, and the bx is this norm c. Okay. So kind of sum x norm b norm c, that's equal to square root sum x norm b squared and square root sum x norm c squared. Okay, so yeah, so this you see norm b squared, norm c squared, and but we already know these two things. This thing is dk, and this thing is 1. Okay, and yeah, so put everything together, then we just know dk plus 1 is let's say equal to is b squared term become dk, and the closed term is 4 square root dk, and square root 1, that's 1, and plus the last term is c squared term is 4. Okay, and so we kind of see the progress. So the progress is the dk plus 1 minus dk is about 4 times square root dk. And okay, so here, yeah, so here we kind of justify what I said before, because the dk makes d makes is at the end is about order n. So this difference between d, so delta d it makes is about square root n. Okay, like what we said. But anyway, so here, so this is just some checking. But anyway, here we do the induction. So induction step, now we can just complete induction step. Okay. So we have a dk minus 1 less than equal to 4 square root dk plus 4. And then we kind of see why we pick a 4 here. Because we have 4k squared here. Then we see that dk plus 1 is less or equal to yeah, so we just plug in everything inside and see things actually check out. So dk plus 1 will less or equal to, so this is 4k squared, and 4 times square root of 4k squared is 2k, and so this is 4 times 2k equal to 8k, and then 4 here, and this is 4 times k plus 1 squared. Okay, so this completes the induction step. And yeah, I think that's the hot power proof. Oh, we are pretty fast. But yeah, so this is the hot step. So we prove that this progress function can grow at most quadratically. And I kind of see that we have 4 here because we know the answer need to be 4 here. But here you can kind of have a feel that the progression is about square root n. So you need order and steps. Okay. Any questions so far? If not, we have a lot of time. We have about 20 minutes. But so 20 minutes we cannot finish everything, but I guess we can finish the other part. Okay, so the other part is not too hard, but yeah, it's intuitive, but we still need to get a proof. Okay, so the other part is we want to say at the end this progress function d at the end it needs to be omega n. Okay, suppose so at the end, suppose there's a big T step, then it needs to be omega n. And okay, and then to prove this, we need to use the fact that, well, the algorithm actually make a decision between yes instance and no instance, right? So suppose the algorithm make a decision based on this projector. So we kind of think at the end, the algorithm make a projective measurement. That's a measurement operator p and 1 minus p. Okay, this is the result of the generality. So yeah. So the end the algorithm will make these projective measurements on p and 1 minus p. And so let's assume it has a pretty good success probability to make our proof here a bit easier. So suppose that okay, it's a bit funny. Or yesterday no instance is kind of reverse inverse. But anyway, so let's assume yes instance we have a very small safe probability. Okay, so I guess let's say P is a reject projector. Okay, it could be funny. Okay. Anyway, so we have been saying this psi with no superscript is yes, and there is no instance. Okay. And so we'll say the P is a projector that will reject your result. Okay. So we say yes instance reject probability should be less or equal to 1/9. It's just some constant. And no instance accept probability should be reject probability should be bigger than 8/9. Okay. So basically, well, anyway, this is some constant. So usually we do like a 1/3 and 2/3 when we talk about probability. When we say like consensus probability, but it can be easily boost amplified to this 8/9 by just run your algorithm B multi and do majority voting. Okay, and yeah, let's assume we have this kind of success probability doesn't change the asymptotic in or it only changes the constant factor in our query complexity. Okay. And anyway, so from here then we can prove that we have constant distance at the end. Okay. Okay. And so we claim that if these conditions are satisfied, then the distance between every pair of psi and psi x must be greater or equal to this constant 2/3. Okay. Yeah, so we need this number kind of high because here we are giving a very simplified proof. Okay. And yeah. Anyway, so let's see the proof. We should have more than enough time to run over this. This is a simplified version. Okay. So yeah, we want to say if so this is a kind of quantum information part. Okay. I guess yeah, we have time, so we can say a little over 15 minutes. It's okay. Yeah, so this is quantum information. So remember, like all the way back to first chapter 1, we say like we have two quantum vector, and you can perfectly distinguish them if only if they are orthogonal to each other. So it's a perfect distinguishment. So in chapter 1, we will say if this is 0 and this is 1, then those two things must be orthogonal. And what we are proving here now is kind of like a more nuanced version of this thing. And here we are saying if you can kind of distinguish these two vectors, not too bad, okay? And then their angle must be. Then they must have a non-trivial angle between them, and so this distance between them must be bigger, greater, or equal to something. Okay. So we are saying if we can distinguish them with constant probability, then the distance between them must be kind of big. Okay. And I think I can leave it here. Okay. And so how we do this? So we actually consider a better distance measure between these two vectors. Because you see that we kind of want to see the angle between them, so how about we just calculate the inner product? Okay. So what's the inner product between A and B? Okay. Okay. Then we okay. Then we start with different things. Okay. So we want to say we have the condition that A applied by the projector is less than 1/9, and B applied on the projector is greater or equal to A/9. Okay. So we think A kind of correspond to 1 minus P part, and B kind of correspond to the P part. Okay. And so we want to say what's small. Okay, so if A apply on P will be small, and so you can reverse this thing, and you can say B apply on the 1 minus p applied on b will be small. Okay. This can be just done by, well, this is just coming from this b squared equal to 1 and equal to 1 minus p b squared plus p b squared. Okay. And yeah, so this thing is big, then this is small. Okay, 1 minus p on b squared. Okay, and so this is small, and here we just take a square root because, yeah, this is kind of a low C part. And so then we just take a square root on both sides, and you see this 1 minus p on b vector is less than or equal to 1 over 3. Okay, and then now we think about the inner product between them. Okay. The inner product between them, we can, once again, we can snug in a 1 minus p and a p pair inside because you have an EP, yeah, because they sum to identity, and then you just break it into two terms, and then by triangle inequality is less than or equal to those two terms. Okay. And then now we see that 1 minus p on b is small and a on p is small. Okay. And so then we break all these inner product even more. So no inner product is less. Okay. So now we use Cauchy-Schwarz. So the norm inner product is less than norm of 2 vector, but we connect the norm to different parts. So we have a norm of A and a norm of 1 minus p on p, 1 minus p on b, and the norm of A on p, so p on A and the norm of b. Okay. And then as we see before, so this thing is small and this thing is small, so this is less than 1/3 and this is less than 1/3. Okay. And yeah, so this norm is small is just from this thing. Okay. And yeah, and so the total thing is less equal to 2/3. Okay, and so we know the inner product is small, then we're going to show something that we claim to be true. So this distance, non-square is actually related to inner product, because if you just expand all this square, then it's a squared plus b squared minus ab minus ba, and it's okay. So those are complex value. But anyway, these are complex value, but then the complex part will cancel out, so we only care about the real part, and it will be greater or equal to 2, so 2 from this non-square because they are normalized vector, minus twice the inner product. Okay. Yeah, because because the most you can subtract is no. Okay. And but we have an upper bound on the inner product, so so we have a lower bound on this distance. So distance is 2/3. Okay. And so this is a very abstract lemma, but what do we want to? So this lemma, we say that we have a projector on A less than 1/9 and a projector on B bigger than A/9, and B distance greater or equal to 2/3. Then we just apply. So P is the same P here, and A is psi t, and B is psi xt for every x. So we see that for every x, this distance between psi t and psi xt squared is greater or equal to 2/3. And yeah, so the total distance is just sum over n of 2/3, so it's 2n/3. And that is a complete proof of optimality of global search. Oh, actually faster than I thought. Okay, and anyway, but as we said, this is not a tight bound. So if you bound this better, and you will see that so if your probability here, so if this thing is if this A/9 here is 1 epsilon instead, okay, so if it is epsilon and 1 minus epsilon here, then what you can get is actually 2 square root epsilon times 1 minus epsilon. Okay. So I think this says as long as your epsilon is constant far away from 1 over 2, then you can have constant distance here. And yeah, so our bound here is actually not tight. We need to be like pretty close to 1 to have this bound, but usually better bound have this. But we don't have time for better bound today, so I think we'll stop early. And yeah, as we say, I think next week I will just let you watch the ISA video from last year, and also do some homework. Okay. And yeah, next week I will be away, and next week we can see a bit more quantum information theory. So this is only quantum information theory we do in this course. So next week we'll see there are 3 ways to next week we're going to see there are 3 ways to prove this thing. So it's a bit of quantum information theory. And yeah, and we will talk about applications of Gilbert's algorithm. Okay, and yeah, so let's stop here for now. No question. Okay, so see you next week.